Welcome, nocturnal minds, aboard. Your learning journey starts now. Right, so we've been looking at how practical concerns shape scientific inquiry. Now, let's zoom in on a specific way scientists handle uncertainty: Bayesianism. Think about those quotes: Spergel betting against Milgram's theory, Kaku talking odds on the SSC finding new particles, Einstein downplaying some theories. These aren't just casual opinions, they're evaluations of probability, often guiding where research money and effort go. The big question is, can we take this intuitive, informal sense of probability and put it on a solid mathematical footing? That's the promise of Bayesianism, named after Reverend Thomas Bayes. He wasn't just playing with numbers, he was trying to make probability a tool for understanding belief itself, showing how to update our beliefs based on evidence. It's like giving formal structure to that gut feeling about whether a theory is likely true. So, how did Bayes actually define this epistemic probability? His idea was quite clever, almost anticipating modern utility theory. Imagine you're offered a bet. If event A happens, you get paid out. How much would you be willing to pay for that bet? Bayes said the probability of A is related to how much you discount the expected payout because of the uncertainty. It's about the value of the expectation versus the value of the thing expected. From this seemingly simple definition, he derived the core rules we use today. If you want your pricing of uncertain bets to be consistent, no one should be able to make a sure win against you by exploiting inconsistencies in your pricing, then probabilities must lie between ling and yi. If two outcomes can't happen together, their probabilities add up. And crucially, the probability of A given B, how likely A is if we know B happened, is just the probability of both A and B happening, divided by the probability of B. These aren't arbitrary rules, they emerge from thinking about rational betting behavior. Now, Bayes' original definition, linking probability directly to monetary value, has a snag. Does getting $10 million feel twice as good as getting $5 million? Probably not. That's where risk aversion and diminishing returns kick in. So, later thinkers like Ramsey and Savage shifted the focus. Instead of money, they talked about pure utility or value. They showed that, if your preferences over gambles are consistent, you can always represent them using a probability function and a utility function. This became hugely influential, but there were other paths. De Finetti took a different tack, focusing purely on coherence in betting odds. If your odds are set such that someone else can't guarantee a profit regardless of the outcome, your odds are coherent, and they correspond to a probability distribution. No need for utility functions up front. Then there's Cox, who approached it from a physicist's perspective. He asked what properties should any reasonable measure of belief A given B have. He laid out some basic desiderata, like if you believe A implies B, then believing A should increase your belief in B, and derived that any such measure must essentially be a conditional probability function PA given B. The author here finds Cox's approach particularly elegant, starting from intuitive principles about belief itself. Okay, here's a classic critique: logical omniscience. Sounds fancy, right? It basically says Bayesianism assumes we're perfect logicians. According to the probability calculus, if a statement is logically true, its probability must be yi. But think about it, can even the smartest person, or even a supercomputer, figure out all logical consequences instantly? Turing and Church showed us computability limits mean even idealized machines can't do that for complex systems. So if Bayesianism demands we assign probability yi to everything we know is logically true, doesn't that make it unrealistic for modeling how real humans who are boundedly rational form beliefs? Some suggested weakening the axioms, maybe only assign probability if you consciously believe something is a tautology. But critics fire back: if you weaken the axioms like that, what's left of Bayesianism as a normative theory of rationality? It loses its teeth. However, folks like De Finetti, the subjective Bayesian camp, weren't bothered. For them, the axioms just define what it means for a set of beliefs to be internally consistent. It doesn't claim agents are logically omniscient, it just says if you are an ideally rational agent, your beliefs should follow these rules. It's about consistency, not computational feasibility. Alright, let's get to the heart of Bayesian confirmation theory, Bayes' theorem. You probably saw this formula somewhere: P of H given E equals P of H times P of E given H divided by P of E. But the text presents a slightly rearranged version that highlights something interesting. P of H given E equals P of H divided by P of H plus B times H minus P of H. Here B is the Bayes factor, which is the ratio of the likelihood of the evidence under the alternative hypothesis, not H, to the likelihood under H. Think of B as how much more likely the data E is if not H is true compared to if H is true. This form tells us clearly your updated belief P of H given E depends on your initial belief P of H and this Bayes factor B. If B is large, meaning E is very unlikely under H, the posterior P of H given E goes down. If B is small, meaning E is much more likely under H than under not H, the posterior goes up. Notice how making P of it given not H small, ruling out other ways it could happen, makes B small, thus boosting the confirmation of H. This sensitivity to alternative explanations is key. This sensitivity to alternatives leads to Lindley's paradox. It's a bit mind-bending. Sometimes standard statistical tests might tell you your data is highly significant, meaning it's unlikely under the null hypothesis, H-ling. But if you apply Bayes' theorem, you might find that the same data actually slightly increases the probability of the null hypothesis. How? Because the test ignores the Bayes factor. If the alternative hypothesis HE is very broad, encompassing many possibilities, then even if the data is unlikely under H-ling, it might be even less likely under HE overall. The paradox shows how ignoring alternative explanations can mislead frequentist tests. Now, let's look at statistical models, where we often have a parameter zeta we want to estimate from data X. The model gives us P of X given zeta, the likelihood. What's fascinating is that, for most models, as you collect more data, the posterior distribution P of zeta given X tends to concentrate tightly around the maximum likelihood estimate, zeta max. Think about flipping a coin n times and getting X heads. The likelihood peaks at zeta equals X divided by n. Even if you started with a weird prior belief about the coin's fairness, after enough flips, the data overwhelmingly pushes your belief towards X divided by n. This convergence is powerful. So, when does evidence E confirm a hypothesis H in Bayesian terms? Simple. If learning E makes H more probable, i.e., pH 大于 pH. Many use the difference, SHE 等于 pH minus pH, as a measure of confirmation. But this simple measure has a weird consequence. If H predicts A perfectly so H entails E, then any conjunction H and also entails E. So, according to S, both H and A are confirmed by E. This looks odd. Why would adding an arbitrary statement strengthen the confirmation? The resolution lies in the math. SH and A depends on PAH. If A is plausible given HP, A is high, and the confirmation boost is bigger. If A is crazy given HPA is low, and the boost is tiny. So, the paradox isn't really a paradox. A bigger headache is the old evidence problem. Consider Mercury's precession. Einstein's general relativity predicted it beautifully after it was already observed. Did GR get confirmed by this old evidence? According to pH 大于 pH, no. Once E is known, PE 等于 E, so pH 等于 pH. The evidence couldn't have confirmed the theory beforehand. This seems deeply counterintuitive to how science works. How do Bayesians tackle the old evidence problem? One idea pushed by Clark Glimmer is that the real confirmation came from discovering the deductive link between GTR and the precession, not from the evidence itself. But this runs into trouble. First, how do you treat whether a logical relationship holds as a variable across possible worlds? It feels philosophically fishy. Second, it doesn't work in general. Imagine you have two data point x, y, and you fit a line through them. You generate a hypothesis L that the linear function determined by those points is the true relationship. Clearly, the data confirms L, even though you didn't discover a pre-existing deductive link. The other main solution is to relativize confirmation. Instead of using your current probability P, Use a hypothetical probability P prime representing your state of belief before you learned E. Since P prime e 小于 1, P prime h can differ from P prime h, allowing for confirmation. The challenge here is defining this P prime E minus. How do you formally remove the influence of E from your beliefs? It's not always straightforward, especially if E was deeply intertwined with other information. But for specific cases, like the Mercury precession, it might be possible to construct such a P prime. Okay, so we've seen how to update beliefs using P of H given E. But how does this connect to the actual process of learning? Is the probability you assign to H after learning E, let's call it P sub E of H, the same as the conditional probability P of H given E? This identification is called conditionalization. It's the standard rule for belief updating in Bayesianism. If you learn E, your new probability for H should be P of H given E. Why accept this? Well, there are proofs, often called Dutch book arguments. These show that if your betting odds don't follow conditionalization, someone else can lay bets with you that guarantee they'll make a profit no matter what happens. It's a strong argument for consistency. While the interpretation of Dutch books is debated, the vast majority of Bayesians accept conditionalization as the correct way to update beliefs. There's also a refinement called Jeffrey conditionalization for when you learn something intermediate, not just a simple fact, E. Now we hit the million-dollar question, or perhaps the million-dollar parameter, the priors. Where do these initial probabilities P of H come from? Unlike likelihoods P of E given H, which often seem grounded in theory or data, priors feel, well, subjective. If a theory H deterministically predicts E, then P of E given H equals E. If it predicts not E, P of E given H equals 0. If H is a statistical model, P of E given H is just the probability the model assigns to E guided by the principle. These seem relatively objective, but for priors? For centuries, people hoped there was a similar objective principle. Could we find a way to determine priors based on some fundamental principles, just like we do for likelihoods? The most famous attempt at an objective prior was the principle of indifference, also called the principle of insufficient reason. The idea is simple. If you have no reason to prefer one outcome over another, you should assign them equal probabilities. If there are mutually exclusive and exhaustive possibilities, each gets probability, E, n. If possibilities are continuous, like the fairness of a coin theta between 0 and E, you use a uniform distribution. Bernoulli called it the principle of insufficient reason, Keynes the principle of indifference. Bayes himself used it, but here's the killer flaw. What counts as a fundamental possibility? It depends entirely on how you slice the problem. Think about transforming variables. Let P be uniformly distributed between 0 and E. Now consider T equals P squared. Both P and T range from 0 to E. But if P is uniform, 'tis not. Its probability density function becomes f of t equals E over R times the square root of t. They can't both be uniform. This arbitrariness means the principle of indifference often fails to give unique, objective priors. So, if indifference fails, what else? E.T. Jaynes proposed maximum entropy. The idea is to choose the prior that maximizes entropy, a measure of uncertainty, subject to any known constraints, like the expected value of some quantity. It aims to be maximally uninformative given the constraints. Sounds good, but finding meaningful constraints is tricky, and it often leads to improper priors distributions whose total probability isn't E. Plus, it can clash with the updating rule conditionalization. Harold Jeffreys took a different tack, focusing on simplicity. He argued for choosing priors that are invariant under certain transformations, like scale changes. For a parameter sigma representing scale, this leads to the Jeffreys prior proportional to the square root of the Fisher information. Again elegant, but it also produces improper priors, violates the likelihood principle, and gives weird joint priors for things like the mean and standard deviation of a normal distribution. Others propose reference priors, designed to let the likelihood dominate early on, aiming for neutrality, but these feel somewhat ad hoc. This struggle over objective priors splits the Bayesian camp. Objective Bayesians like Jaynes and Jeffries insist that without some objective way to pin down priors, the theory is just subjective opinion. They need principles to constrain the choices. Subjective Bayesians, following De Finetti, Ramsey, and Savage, take a different stance. They say, look, the quest for perfectly objective priors is doomed because it's circular. How can you justify a principle for choosing priors without already assuming something about rationality or belief? Their view is that Bayesianism is fundamentally about consistency. Just like logic doesn't judge the truth of your starting premises, but checks if your conclusions follow logically, Bayesian probability theory checks if your belief updates are internally consistent. As Ramsey put it, it's about declaring which conclusions are the only ones consistent with your prior beliefs and the evidence. De Finetti echoed this: the logic of probability helps see the implications already contained in what came before. It's about coherence, not finding an objectively correct starting point. If priors are subjective, how can science ever reach objective agreement? This is where convergence of opinion theorems come in. These powerful results show that, under fairly general conditions, as you gather more and more data, your posterior belief P of H given E will converge towards E if H is true, and Ling if H is false, regardless of what your initial prior P of H was. Even stronger versions state this convergence happens with probability E. This seems like a mathematical solution to Hume's problem of induction. But there's a catch. These strong results often rely on the axiom of countable additivity. This axiom extends the probability rules from finite sets of outcomes to countably infinite sets. Its status is controversial. De Finetti rejected it, arguing it imposes arbitrary restrictions like forbidding uniform distributions over infinite sets while allowing them over finite ones, just for mathematical convenience. If De Finetti is right, then these seemingly objective convergence results might be artifacts of a purely mathematical assumption, not reflecting the epistemology of belief itself. Despite the debates, Bayesian ideas haven't stood still. They are being applied in exciting new ways. Take Bayesian networks. These graphical models represent probabilistic relationships between variables. Philosophers like Williamson are using them to tackle thorny problems like causation, trying to build a theory of causality within a Bayesian framework. Others, like Bovins and Hartman, use them to argue formally why bodies of belief that are internally consistent should be considered more reliable than those that are contradictory. It shows that the core ideas from Reverend Bayes are still being explored and adapted to address cutting-edge scientific questions. All right, shifting gears completely. Let's talk about computer simulation. We hear about it everywhere now. What exactly is it? In its narrowest sense, it's about using a computer to run a specific kind of algorithm. This algorithm solves mathematical equations, usually differential equations, that describe how some system changes over time. Think of weather forecasting. You start with the current temperature and pressure. The computer solves equations predicting how they'll change hour by hour, day by day. It iterates step by step through time. The output is a sequence of snapshots showing the system's evolution. Often, we see this as graphs or animations. Key things to note: it's iterative. It often involves approximations since exact solutions are rare for complex systems, and the results can vary slightly depending on the exact computer and software used. But we usually mean something broader when we talk about computer simulation in science. It's not just the running part, it's the whole enterprise building the model, running it, checking the results, and figuring out what it tells us about the real world. That's the philosophical sweet spot. We can broadly distinguish two types. Equation-based simulations, common in physics and engineering, use mathematical equations to describe the system's behavior. Think fluid dynamics equations for weather. Agent-based simulations, popular in social sciences and biology, model individual entities, agents, and their interactions. Imagine simulating a coffee bean supply chain not with equations for bean volume, but by modeling individual workers following simple rules like deliver beans if truck is loaded, stay home if too many sick colleagues. The cool part is seeing complex patterns emerge from these simple agent-level rules. Economics uses both. Epidemiology often does. Sociology leans more towards agent-based. Why bother with all this? What do scientists hope to get out of simulations? Three main goals stand out. Prediction is obvious, forecasting the weather, testing if a new airplane wing will perform as designed. Understanding is another big one. Detailed simulations of thunderstorms help explain why they split or spawn tornadoes, acting as a virtual laboratory when real observations are hard to get. Finally, simulations are great for exploration, especially when we don't have a strong theoretical grip on a system. By tweaking simple rules in an agent-based model, maybe we can accidentally reproduce patterns seen in real societies, sparking new hypotheses about why those patterns exist. It's a powerful heuristic tool. Okay, so we run simulations, get results, and then make claims about the real world. But how do we know if those claims are justified? What's the epistemology of computer simulation? Winsberg laid out three conditions any good epistemology needs. First, it must acknowledge that often simulations are built on top of existing scientific theories. Theory provides the foundation and helps validate the simulation's conclusions. Justification flows downwards. Second, it must be motley. Simulation results depend on way more than just the core theory, numerical methods, parameter choices, coding tricks, even the compiler. The justification process is messy and multifaceted. Third, it needs to be autonomous. We often simulate things we can't easily observe directly, like the early universe or ethical experiments. The epistemology must allow for justification, even with limited direct comparison to reality. In fields like engineering, people talk a lot about verification and validation, or V and V. Verification asks, did we solve the equations correctly? Did a code implement the math accurately? Validation asks, did we solve the right equations? Does the model actually capture the relevant aspects of the real system? Verification often involves checking against known solutions or ensuring numerical stability. Validation typically involves comparing outputs to real-world data. Sounds neat, right? Verification versus validation. But philosophers have raised eyebrows. Winsberg argues they're often mixed up in practice, and verification alone doesn't give much confidence. Trust comes from seeing both verification and validation efforts align. Oreskes and others pointed out that terminology is misleading. Calling a model validated suggests we've proven it's true, which is hubris. Models are complex hypotheses. They can be confirmed by data, but never proven true. Parker adds another layer. We rarely test if the model's assumptions are literally true, but rather if the model is adequate for the specific purpose we're using it for, which can be surprisingly difficult. Scientists often proudly call their work computer experiments or in silico experiments. This raises a fun philosophical question. Are they really experiments? Some say it's just shorthand, meaning the simulation study replaces a traditional experiment, but it's not an experiment itself. Others argue they aren't genuine experiments because you're manipulating a model, not the real thing. But wait. Don't we do that all the time? Rat studies aim to learn about humans manipulating a model organism, so that objection seems weak. Maybe they are virtual experiments, interventions on mathematical models, but then how do we intervene on abstract equations? And it ignores the concrete computer hardware involved. Parker offers a bolder view. Yes, they are genuine experiments. The intervention is on the computer system setting initial values, changing parameters, running the program. The goal is to learn about the target system. This seems broad, maybe too broad. The debate highlights differences in how we conceptualize the relationship between models, computation, and empirical knowledge. Does computer simulation shake the foundations of philosophy of science? Some say it's just the same old problems in a new guise. Frege and Rice call it the same old stew. Others disagree, arguing it does raise new questions. There's continuity. Simulations are imperfect models, so questions about inference and external validity arise just like with lab experiments. But there are new twists. How much do computational limits force compromises in model design? Debugging a complex simulation is hard figuring out if a bug is in the physics or the math is incredibly difficult. More profoundly, Humphreys and Winsberg argue simulation challenges core views of theories. Often, we use simulation to apply theories we already have, like using fluid dynamics equations for weather prediction. This challenges the semantic view which says only the meaning of a theory matters, not its linguistic form. Syntax does matter. The specific equations you use to simulate can drastically affect results. It also challenges the syntactic view which sees theory application as logical deduction. Simulation application is opaque, approximate, and computationally intensive, hardly a simple deduction. Agent-based simulation throws in another layer of philosophical complexity, especially regarding explanation. Some social scientists, like Epstein, have famously equated, "Can you explain it?" with "Can you grow it?" Their idea is that if you can build an agent-based simulation that reproduces a social pattern like market crashes or segregation, then you've explained it. This raises immediate questions. Does successfully simulating a phenomenon constitute an explanation? If yes, what kind of explanation is it? Is it showing the potential mechanism or demonstrating a causal pathway? Or is it more like showing a functional explanation? The relationship between simulation success and explanatory power is still hotly debated. The field is definitely expanding. There's a growing body of work applying philosophy of simulation specifically to climate modeling, grappling with deep questions about uncertainty, risk, and the role of values in assessing climate projections. Another exciting area looks at how simulation partners with other scientific practices. High-energy physicists use simulations extensively in designing detectors and analyzing particle collision data. Geophysicists increasingly blend simulations with real-time observations through data assimilation to create better weather and climate reanalysis. Understanding these intricate partnerships between modeling, simulation, and experimentation is a rich avenue for future philosophical work. So, wrapping up, we've journeyed through Bayesianism from its roots in quantifying belief to the ongoing debates about priors and logical omniscience, and seen how it connects to convergence and modern applications. Then we moved into the world of computer simulation, exploring what it is, how it's used, the tricky questions about justifying its results, and whether it truly represents a new kind of scientific practice. Both areas highlight the evolving landscape of scientific reasoning and the persistent need for philosophical reflection.